So today we're going to be talking about measurements and how we record our measurements depending on what instruments we're using to take those measurements, what are the units that we use, how do we round and do calculations with numbers that we're working with, a concept called scientific notation, which is a specific way of writing numbers that are either really big or really small. We'll talk about concepts of accuracy and precision and error, okay, and how we deal with all of those things and what they all mean in the context of this class. So first of all, what is a measurement? Well, a measurement has to have two parts. It has to have a number, say 70, and a unit, like centimeters. So it's not a measurement without both of those things, right? Centimeters is just a unit. It's a unit for measuring distance or length. 70 is just a number. It could mean anything. But when you put them together, it's a measurement, say, of the length of a lab table, or 4.2 kilograms. Right? That's a measure of mass, which might be the mass of a really thick textbook, like one of the ones that we use. So every measurement in this class should always have a number and a unit. Otherwise, it doesn't communicate the information that we need. So always put units with your numbers. That will be true in 99.9% of the cases. There's a couple of exceptions that we'll deal with when we get there. So that's what measurements are. Why do we measure? Well, we measure so that we can communicate that information. Right? What was the length of the table, or what length do you need the table to be if you're sending it to someone who's going to build you a desk or order you a table? How much does the book weigh? Right? You might need that for packing information or shipping information. Or in the scientific community, we record these measurements and we deal with units that are universal or international, so that if I take a lab and write out down all my information here in the United States, and someone over in Europe or Asia or anywhere else in the world reads that information, they can understand and compare what they are doing to what I'm doing. They can try to replicate what I did or alter it in some way to see if they get the same results, but we're all speaking the same language in terms of numbers and units. So another concept that we need to talk about is accuracy and precision. A lot of times these things get used interchangeably, but they don't mean quite the same thing, especially in the context that we're talking about. So accuracy is how close is a value to the accepted value, or, for lack of a better word, the right answer. Okay? So how close did you get to the correct number? The problem with accuracy is if you think of it in terms of, say, aiming at a target, right? You want to get close to the bullseye. But if you're taking measurements, you might have a measurement here and a measurement here and a measurement here, and when you take the average, you end up with something close to the right answer. But it's more or less by luck. So you can arrive at an accurate value as the result of a bunch of inaccurate measurements. So that's accuracy, means you get the right answer. Precision, again to use the bullseye, precision means you take a series of measurements and they're all close together. Right? So accuracy measures your answer in relation to the correct answer. Precision measures your answers in comparison to each other. So did you get the same answer every time? We do 3 trials in a lab. Do you come out with the same result? The problem with precision is I could get the same answer or close to the same answer every time, but they might not be anywhere near that right answer. So we want to be accurate. We want to get the right answer, but we want to get that answer every time. So you always want to have accuracy and precision together. So you hit that bullseye every single time. So the next concept we want to talk about with measuring and uncertainty and precision and accuracy are concepts called error and percent error. So the error is just how far was your answer from the accepted value. So you simply take your answer, which is called the experimental value. What did you get when you did the experiment? And then you subtract the correct answer or the accepted value. There's a difference there. How far were you in numeric terms from the correct answer? It could be positive or negative, because if your answer is smaller than the accepted value, you have a negative error, which tells someone reading it that your answer was below the correct answer. If you have a positive error, it means your answer was above the correct answer. But it's helpful in that it tells you how far off you were, but it doesn't give you any sense of context. Right? If I say I was off by 10 centimeters, that's my error. Okay, so my measurement was 10 centimeters away from the correct answer. But it doesn't really tell me relative to what? What was the correct answer? How big was this mistake really? Well, if the correct measurement, let's say again I'm measuring length, if the correct measurement was 5 centimeters, well, my error is huge, right? I was actually off by more than the measurement. I measured it double what it should have been. But if that measurement of 10 centimeters was out of, say, 10,000 centimeters, well, that's a fairly small error in comparison. So we use another concept called percent error to give an estimate of how far off we were in relation to the answer itself. So to find the percent error, we take the error, so if this was the error up here, we take the absolute value, and all that means is there's no negative percent error. So if you have a negative 10 centimeters, the absolute value of that is just 10 centimeters. So we just drop that minus sign. So we take the error, and then we divide it by, in this case, if I use 5 centimeters, 10 centimeters divided by 5 centimeters times 100. So this is very similar to what you do if you, for example, take a quiz and it's out of 5 points, let's say. You take your score, divide it by the possible score times 100, you get a grade of 80, 90%, whatever your score was. The difference here is instead of measuring how many points you got, we're essentially measuring how many questions you missed. So your error instead of your correct score. Okay, so that's percent error and error. And now we're going to talk about how we actually record our measurements based on the instruments we're using and how many decimal places and things like that we want to record, which is a concept called significant figures. So significant figures is a concept that we use because the measurements that we take are in part determined by the instruments we use to take those measurements. There's no such thing as a perfect ruler or a perfect scale. So we're limited by the tools we're using. And there's different tools for different types of measurements that have more or less precision and accuracy. So for example, if I have a ruler, let's say, that has, let's say this is 1 meter long. So it starts at 0 meters and it goes to 1 meter. And let's say I'm measuring a box like this. Okay, so I can use this ruler and I can measure it, okay, right down to here. And I might say, well, that looks like it's a little more than halfway. Okay, I know it's more than 0 and I know it's less than 1 because the ruler has those markings on it. But in between, I have to sort of guess. I have to estimate. So I would write this measurement as 0.6 meters. Now, the 0, like we should all be able to agree because the markings are there, that it's between 0 and 1. So the first digit is significant because it's an agreed upon number. Then you always want to go one place beyond the smallest marks on your tool. So in this case, the smallest markings are at the 1s, so I want to estimate to the 10ths. Now this number here, because it's an estimate, that could vary from one person to the next. Maybe you think it's more like 0.7. Maybe you think it looks like 0.5. We all agree on the 0. That second number, because it's an estimate, could vary from person to person, and there's really not much you can do to argue that point. Now I can't say 0.65, for example, because the 0.6 is already an estimate, so adding any more digits after that is just completely making things up, and it's not what we do in science. So that would be one measurement, and then if I had a better tool, so let's say I find another ruler, and it's got markings at every, it's not perfect, but so these are markings at the point in the tenths place. So it goes 0.1, 0.2, 3, 4, 5. So this is 0.6 and this is 0.7. Well, now that we have these additional markings, now we should all be able to agree that it's between 0.6 and 0.7. So now I have 0.6 for sure, and now I'm going to estimate in between one more place to the 0.63 meters. So now the hundredths place is my estimate. The 0 and the 6 are the things that we're sure of. So anytime you have a measurement, whether it's a ruler or a beaker or a graduated cylinder or a scale, you need to look at what's the smallest marking on that tool. Is it the tens, the ones, the tenths, the hundredths? Sometimes it's even the thousandths. Whatever that last marking is, you want to go to that decimal place and then one more. And that's it. No more, no less. Right? Estimate one last thing in between the marks. If you think it's exactly on the mark, this is important. Let's say I thought this was exactly on the 0.6, which it's not. But I would write that as 0.60 meters. Again, including that extra zero tells anyone looking at it that I'm guessing it's right on the 0.6, but maybe the next person might look at it and says, no, I think it's 0.61, or I think it's a little bit below it, it's 0.59. Okay, so that last digit is up for debate. If I think it's right on the line, you always add the zero. Okay, so just keep that in mind. So when we're taking measurements, we talked about you want to write down all the digits that you know, so all the markings on your tool, and then estimate one extra digit as a in-between. But what if you're just looking at numbers and you want to do some calculations with them? How do you figure out what are the significant digits and what are not significant digits? Because that will matter when we talk about rounding. When we talk about what's a significant digit, there's only a couple of rules that you really need to keep in mind. And depending on where you look, you might see 4, 5, or 6 different specific rules for significant figures. I try to keep it to as few rules as possible. So I'm going to summarize, and if you look it up in the book or online or whatever, you're going to find different combinations or different ways of explaining what I'm going to say. And there's nothing wrong with any of them, but I always try to keep the list of rules you have to remember as small as possible, just because why not? So the first thing you need to keep in mind, and the easiest rule to remember, is that any digit that is not a zero is a significant figure. Okay, so that's the easiest rule of all. If it's not a zero, you count it as a significant figure. So this number here has 4 significant figures. And why do we care how many significant figures there are? We're going to talk about that in a minute when we talk about calculations and rounding, because that's going to come into play. So if anything that's not a zero, so 1 through 9, always counts, then really what you need to figure out is, what about the zeros? When do the zeros count and when do they not count? So there's a couple of rules here, but the simplest way I can explain it is, if you have zeros to the left of non-zero numbers, so when would that happen? Well, it would happen if you had, for example, 0.0023. Okay, these zeros are to the left of the 2. We call these leading zeros. Right? They're just there because I needed that 2 to be in the thousandths place instead of the tenths place, for example. So they're just holding the places. So they're not considered significant figures. So this number here only has 2 significant figures. These zeros are not significant digits. Zeros on the right of a number, so they're called trailing zeros, do not count as significant figures unless there's a decimal point. So a number like 12,000, for example, there's no decimal point anywhere in that number. So these are zeros to the right, they're trailing zeros in a number without a decimal point. They are not considered significant figures. So this only has 2 significant figures. Okay, so the zeros don't count on the left ever. So if you start on the left and the first number you see is a 0, well, you don't count anything until you get to the first number that's not a 0, and then you count everything to the right. If you start on the right with no decimal point, so the first thing to look at, is there a decimal point? No? Well, then look at the right. Is the first number you come to a 0? If that's true, then you keep going until you get to something that's not a 0, and you count everything beyond that to the left. Okay? So the other cases where you could have things are something like 1034. Okay, this 0, it's not on the left, it's not on the right, it's in the middle between other numbers. That's called a sandwich 0 or a bookended 0. So that counts. Okay, so this would actually have 1, 2, 3, 4 significant figures. So if it's not on the left and if it's not on the right in a number without a decimal point, the 0 in the middle counts. And it could be 10304 or even 10004. Right? Any zeros that are in between 2 other numbers count as significant, no matter how many zeros are in between, or if they're broken up like this. Doesn't matter the order. If there's a digit on the left and the right of a 0 that's not a 0, you count all the zeros in between. The other time that they'll count, something like 010, or we had 0.60 a minute ago. Well, these numbers, these zeros are on the left. They don't count. So you count, they don't count that, I don't count this. I count the 1, and then I count everything after that. So even though this is on the right, the fact that there's a decimal point here makes this a significant digit. So this has 2 significant figures. I forgot to write this one. It would have 5 significant figures. So the zeros are the only thing you really need to think about, is do they count or not? And it's determined by where are they, left or right, and is there a decimal point? Zeros to the left never count, and the only time you see them is with a decimal point. Zeros to the right don't count if there's no decimal point anywhere in the number. It doesn't matter where. If the decimal point is here, those still count. Decimal point means zeros to the right count. Or something like this. Okay, the decimal point, and these are in between, so let's just add another 0 over here. Okay, so don't worry about this right now. So these zeros, even though they're to the left of the decimal point, it counts because it's still in between 2 other numbers. So you have to kind of look at each rule one at a time. Is it a 0? No, if it's not a 0, it counts. Is it a 0 to the left? There's no non-zero numbers on the left of that 0, then they don't count until you get to something that's not a 0. Are the zeros on the right? Well, is there a decimal point? If there isn't a decimal point, zeros to the right don't count. Is it in between? It counts. Is it on the right, but there is a decimal point? It counts. That sounds like a lot of rules, but if you try to keep it to non-zero always counts, to the left never counts, and to the right doesn't count if there's a decimal point, or if there's no decimal point, that really kind of keeps it to 3 rules. And all the other ones just fall in between. So we've learned about how to figure out what's a significant figure and what isn't. So then the question is, well, why do we need to know that? If we're measuring them, we've discussed how you write the correct number of significant figures, but why do we need to just look at a number and know how many significant figures there are? Because when we do calculations, which we will often be doing with these numbers, we need to know, how do I round? Because you could put a value into the calculator and ask it to multiply, divide, add, subtract, and you might get an answer with 15 digits, and you want to say, do I need all those? How do I round? Where do I round to? Very common question. Well, there's a couple of rules that you need to keep in mind, and it depends. Are you adding and subtracting, or are you multiplying and dividing? There's just 2 different things that we do. So let's start with adding and subtracting. So when you're adding some numbers, let's say 121.5, 32.11, and 119.052. Okay, and then I'm going to have to hopefully do this math correctly. So when we add this up, we get 2, we get 6, 6, decimal point, that's 12, carry the 1, that's, so not 8, it's 7, and then this would be 2. So when I add these up or put them in the calculator, I get 272.662. That is the full and complete answer that you'd get. However, I can't report my answer that way because of the rules. And the rule says that when you're adding or subtracting, it would work the same, we're adding here, but if I was subtracting, it'd follow the same rule. Your answer cannot have more places than the least precise number you started with. And what does that mean in reality? It means look at the decimal places, or even if there wasn't a decimal, look at the ones or the tens. What's the last place that each number has? And if you line them up like this when you're writing them down with the decimal point together, it's pretty simple to see that this only has 1 decimal place. That means that my answer cannot have more than 1 decimal place, so I round to that decimal place. So I'd actually finally report this as, right, I'd round it here, since this is a 6, I round up to 7. 272.7 would be my final answer. And I know this doesn't have a unit, but I'm focusing on the numbers right now. So the reason for that is, because there's nothing here and nothing here, I don't know really what these numbers would add up to, because I don't have the information. So I have to go with the one place, or the last place that I'm sure of in all my numbers. So that's the answer to the question, how many places do I round to? You round to the last place you're sure of when you're adding and subtracting. Multiplying and dividing has a slightly different rule. So when you're multiplying and dividing, the rule doesn't care about the decimal places, right? So in adding and subtracting, it's the last place that you're sure of. But when you're multiplying and dividing, it's just how many significant digits does each number that you're multiplying or dividing have. So what does that mean? Well, if I take, for example, 12.5 times 4.5, okay, and hopefully I'm going to do this right in my head. So 12 and a half times 4 would be 48 plus 5 times 4, so 50. And then times a half would be 56.25. Okay, so that's, again, the number you get when you put this in the calculator is 56.25. The rule says your answer cannot have more significant figures than the number that you started with the fewest significant figures. So this has 3 significant figures. This has 2 significant figures. So I'm going to have to round my answer to only 2 significant figures. So here's significant figure 5, 6. That's it. That's all I can have. So I'm going to look at the next digit. It's a 2. So I'm just going to round that off and report this as 56. Okay, if there were more digits, I would keep going, and I would round to whatever number. If this had 4 and this one still had 3, then I would round to 3 digits, and I'd report it as, actually it'd be 56.3, because I'd round up. Okay, the rounding up and down rule is the same you've always known. If it's 5 or greater, you round up. If it's not, you just leave it. So you don't keep the decimal point, even though it was there in your answer. If it's 56, you just write it as 56 and leave it there. And I added that extra digit. Okay, so adding and subtracting is about the last place that you're sure of in terms of tens, ones, tenths, hundredths, thousandths, whatever that number is. When you're multiplying and dividing, it's just how many digits does each value have? Round your answer to the smallest number of digits. All right, so the last concept in this section is something called scientific notation. What is it, why do we need it, and how do we use it? Well, scientific notation is a way of sort of condensing very, very large or very, very small numbers, which we use a lot in chemistry. For example, this number is the number of atoms in a single gram of hydrogen gas. It's a huge number, all those zeros. And this number is the number of grams that each one of those atoms weighs. So it's a super small number, decimal point, all these zeros. Now, we very often have to work with numbers like this, and then we have to, for example, multiply this number times this number to figure out how much do all these atoms weigh if you multiply them together. And can you imagine trying to put all those zeros into your calculator and make sure you're keeping track? You have to count all the zeros. Some calculators won't even let you put in that many numbers. Okay, so we need a way to simplify this so that it's easier to work with. It's also a pain in the neck to write all these out. So we condense these using scientific notation. Every number in scientific notation has 2 parts. There is a coefficient, which has to be a number between 1 and 10, so a single digit number. It might have decimal places, but it can only be a single digit to the left of the decimal. And then the second part is multiplying it times 10 with some power, so a power of 10, an exponent. So what does that mean? So if we take a look at the number of atoms and we rewrite it in scientific notation, it would look like this. (6.022) times 10 to the 23rd power. So what does that really mean? Well, the 6.22 is if I start with the number of atoms, and the decimal point, which is way over at the end, gets moved over until it ends up with only 1 digit to the left, the 6. And I'm going to keep the other digits that are here and just drop off the rest of the zeros. Well, the difference between this number and the expanded or standard notation is that I had to move the decimal point 23 times. That's where this number comes from. So the power of 10, the exponent of 10, is how many times did I move the decimal point to get it from where it started in the regular notation to where it ends up in the scientific notation. So just to sort of simplify that a little bit with a little bit more reasonable number. The number, say, 3,100. Okay? Well, if I want to make this in scientific notation, the first part is to fix the coefficient or to create a coefficient. By taking the decimal point, which is really here, I move it 1, 2, 3 times. So I end up with 3.1 times 10 to the 3rd power because I moved the decimal point 3 times. So if you think about that, again, this number is a ridiculous number to think about, but 10 to the 3rd power is 1,000. So what I'm really saying here is 3.1 times 1,000. Well, that's 3,100. Okay, so I'm just abbreviating the number written out like this using the powers of 10. Using the powers of 10, which is really what all the decimal places represent. Every time you move the decimal point, it's multiplying or dividing by 10. Okay? Now, just to look at an example of what we do with the decimals, like the number of grams of a single atom, let's take a slightly simpler number like 0.00135. Okay? In order to get this into scientific notation, I have to change this decimal point or shift it until there's one digit to the left. So that means 1, 2, 3. That would be 1.35 times 10. I moved it 3 times, but because I moved it in this direction, because I started with a number that was less than 1, I make it a negative 3. Okay, so the negative exponent indicates that this was a decimal to begin with. The positive exponents up here tell me that this number was a bigger number to begin with. And that's the only difference. It's always, the number is the number of places you move the decimal point. Whether it's left or right, that's the number. The positive versus negative is, well, was it a big number to start with or was it a small number to start with? If it's a decimal, you use a negative. If it's not a decimal, you use a positive. A couple of quick things that people will often do when you're starting out with this especially is you just count the zeros. Right? Well, I get rid of the 2 zeros, so that must be a 2. And they forget that you still have to move that extra third place to get the decimal point between the 3 and the 1. Or when you're counting, again, you count the zeros. You don't count this 0 because that was already over there past the decimal point. You also don't want to go 1, 2, 3, and then keep going to the very end because that's not where you put the decimal point. The decimal point goes between the 1 and the 5, so that's where you stop counting. So these are just common mistakes that I'm trying to give you a little bit of a heads up. Hopefully it will help you avoid those mistakes when you're starting this. So that is the end of this part of the unit. We've talked about accuracy, precision, error, percent error, significant figures and how we measure with them, how we calculate and round with them, and then scientific notation in order to abbreviate very large and very small numbers, which we use all the time in chemistry. So we're going to practice this a lot, and we will use these concepts all year long. So if you don't get it yet, you're going to have a lot of time to practice, and it's something, these rules and these calculations and rounding things are going to come up all year long. The good thing with the scientific notation especially, I think I mentioned this, is that your calculator can do a lot of this work for you. So you don't necessarily have to write this back out in expanded notation, calculate, put it back into scientific notation. You can put this into the calculator in scientific notation if you wanted to multiply these two numbers together, and then the answer will come out of your calculator already in scientific notation, and I will help you learn how to do that using the right combination of keys when you're entering it. So that's the lesson for today.